Hello, my name is Askeland. This is my 8th video about Riemann's hypothesis. What you see is the Tic Tac Clockwork of prime numbers. This image explains a lot of connections in Riemann hypothesis theory. It explains that Riemann's functional equation is a conditional equation which only can have zeros on the critical line. It explains that Riemann's hypothesis is true. It explains that analytic theory cannot be used to solve Riemann's hypothesis. I will in this video explain how Askeland's condition can be used to find Riemann's analytic continuation discretely through the zero crossings of the phase diagram of the Euler product. What you hear now is the Tic Tac Clockwork caused by prime numbers. I will in this video try to show you all these connections. This is Riemann's zeta function as a sum formula. As you see, I've chosen the length to be a prime, which in this case is 9973. Riemann's zeta function can be rearranged to the Euler product, which looks like this. The phase diagram of the Euler product has this formula. This is the plot of the phase of the Euler product on the critical line when the max prime is 9973. The blue curve is the phase of Riemann's analytic continuation. A vertical jump is a Riemann zero. This is 0, 1, 0, 2, and 0, 3. As you see, we can find the same zeros in the lower plot, but they are not so precise. And if I add some lines through the oscillations, these lines follow Riemann's analytic continuation. In this part, you see two vectors rotating with the same frequency as the frequency of the Euler plot. The frequency is the same. The red vector rotates counterclockwise. Attached to the red vector is the left side of Riemann's functional equation. This is the formula for the red vector. Equation 11 from my Riemann hypothesis proof in video 1 is a functional equation of the zeta sum formula which contains a condition. The condition is infinite outside the critical line, but can cancel by subtraction on the critical line where the real part of S is 1/2. The condition has a solution as shown in equation 35. The condition is then 0 for discrete values of b. And for these discrete b values, the sum formula is expressed as Riemann's functional equation. And these discrete b values can be found with the phase equation inside the green frame. Small g of zero's contribution to a solution is given by the right-hand side of equation 35. I move this part of the solution to the left-hand side so it's added to the zeta function. So now it drives the zeta function around in counterclockwise direction. Attached to the blue vector is the right-hand side of Riemann's functional equation. And this part is driven by the other side of equation 35. The blue vector rotates clockwise. They pass each other inside the red frame at 3 o'clock and at 9 o'clock. They cancel by subtraction, which is a condition for Riemann's functional equation to be true. The vectors meet at 3 o'clock, where Riemann's functional equation suddenly is true. When b equals 11.77 and n equals 9973, Riemann's functional equation can be solved. Riemann's functional equation will also solve at 9 o'clock. In this case, b equals 12.79. The length of the vectors are the same on the critical line. Outside the critical line, the length of the vectors are different, and one of the vectors will go sooner to infinity as n goes to infinity. Vector cancellation can therefore not take place outside the critical line, which proves the hypothesis. Riemann's functional equation is a conditional equation which only can be solved with factors on the critical line. The equation has to line up in order to solve it. This equation finds the b-values where the vectors meet and where Riemann's functional equation can have factors. Riemann's functional equation is therefore an equation which only can give zeros on the critical line. And that's the logic of my Riemann hypothesis proof. When I solve the equation, I find the zero crossings of the Euler product. Let's run the plot again with the solution of Askeland's condition for n equals 9973. So I solve Askeland's condition for every k value. And this b value will find one zero crossing of the Euler phase diagram. The plot now matches Riemann's analytic continuation discretely. Before I continue, I would like to show how complicated Euler's phase diagram is. I will now show how the Euler phase changes with the maximum prime. You can now see that the amplitude is increasing. It also seems like the wave is moving to the left, but that's just the increase of the oscillation frequency. It becomes more and more difficult to see Riemann's blue analytic continuation. It would not be a great discovery if I only could factorize the zeta function for n equals 9973. The zeta sum formula is a limit, so the theory must also comply as n goes to infinity. I have now increased n to approximately 100 millions. That doubles the oscillation frequency. The increased frequency can be seen inside the Euler phase diagram as a denser plot. But now the Euler phase has large waves. We can no longer see traces of the Riemann's blue analytic continuation. The continuation has drowned in the phase waves. Now we need Askeland's condition to find the analytic continuation. Enter lowest prime below 100 millions into Askeland's condition. Then solve for every natural number k. Then enter each solution into the Euler phase formula and plot the result in the upper plot to see if it is the same as Riemann's analytic continuation. Now the tic-tac clock of the primes goes twice as fast. And Riemann's analytic continuation can be discretely observed through the zero crossings of the Euler phase diagram. The reason why Riemann's hypothesis cannot be solved with Riemann's theory is that Riemann drops infinity from his equations. It's unfortunately in the infinity terms the condition for a solution of Riemann's hypothesis lies. Although Riemann's hypothesis is true, analytic theory will never solve the hypothesis. Riemann left the condition in his trash can. But Riemann's hypothesis is true since there is a self-destructive oscillation inside the zeta sum formula, which makes it possible to calculate convergent zeros. These convergent zeros are the same as Riemann's analytic zeros since they follow Riemann's functional equation discretely. Conclusions. Riemann's zeta sum formula can be expressed as equation 11 with a condition. The condition rotates Riemann's functional equation on the critical line. The rotation lines up the functional equation at 3 o'clock and at 9 o'clock. At these discrete values, the functional equation of the sum formula complies with Riemann's functional equation as an analytic continuation. The condition removes itself with Riemann's analytic theory from 1859. Riemann left the condition in his trash can. The condition cannot be recovered once it's gone. That's why Riemann's hypothesis is unsolvable as an analytic continuation. So mathematicians are trying to solve a problem which is solvable, but they are not using the right method. And they do not seem to listen to ideas from outside their community. I will in my next video tell the history of my proof. The story started already in 2005 and is still going on. Thank you for watching.